So that's where we're going. I thought I'd take a little break from just the pure math and just think if you online somewhere you might have seen very artistic, something that kind of looks like this. In the news, big news lately. What is this? What is this ridiculous photograph on? Yes?
Hi, I wanted to ask what the midterm sections will be covered. Just not the like kilowatt section.
Well, it'll only cover sections we actually cover,
Oh, yeah, but
and you want to know what that will be up through.
yes.
I can answer that. I think I posted online somewhere a tentative schedule, which is now out of date, but 3.6, rational functions is the last section. It might be on the exam.
Thank you.
Okay. When this, even recognize what I'm drawing here. Students are too busy to look at the news. This is supposed to be the Webb telescope. You've all heard of this?
Oh. Yes.
I know, my artwork is not that good. Now does it?
Yes. Now you said it.
Yeah.
It sounds
And we have this big old mirror here. It's actually made of pieces. You want to know the shape of the mirror?
Concave. Concave, maybe. Concave mirror.
It is concave, yes. Can we be more specific? Yes?
Wait, can I ask a question about when the midterm is? When is the midterm?
The midterm, it's the Thursday after break. What day is that? It is the 20th. Thursday the 20th of October.
Thank you.
Concave. Anybody know any more about the shape? Yeah.
Is it an octagon?
Is it optical?
Is it an octagon?
Ah, well, the outer shape is an octagon, that's true. That has to do with the fact that when they made it, I think they're either hexagonal or octagonal pieces. I think they're hexagonal, actually. That, draw a nice hexagon. And draw another nice hexagon. Draw another nice hexagon. We got another one. These are all exactly the same size, right? And then we got another one here, another one here, another one here. And they fold up nicely, and then they fit together nicely. But I'm thinking more like along the lines of, yeah, it's concave, but in particular, does anyone know the shape? Yes?
Like the hexagon or the honeycomb?
The honeycomb on the back of these hexagonal things. You know, I don't know if these are made of glass or metal. I think they're metal. Usually telescope mirrors are glass. But down below, it's not solid. There's a honeycomb shape to lighter, to kind of carve out the insides. Really, I'm thinking of just the surface that, is is facing out into the night sky. One, I guess not. Okay. This is a parabola. I don't know if there's anything I can do with it here. This is actually a little telescope there. If you want to come up later in class and take a close look. It's pretty old and dirty, so you can't really hurt it. These are very delicate, though. They're covered over with a thin layer of aluminum or silver. And it's a parabolic shape, which means if you see your face in the back, it's upside down, right? Okay,
Yeah.
someone's shaking their head up.
Yeah.
But if you look at it here, it's right side up. Right?
Why is that?
Well, first let's go at, we're going to answer that. First we'll go at why do we use these for a telescope? Well, parabolic shape has the feature that, you know, light bounces off the edges. Light that comes in parallel bounces off the edges. And it all passes through one point, which we call the focus. Now, of course, it's hard to get out here and see, so typically we use some methodology. We might put a detector here, or we might, a little further up, we might put we call it diagonal mirror, so that the focus ends up out here where we can see it. But because of this, if you are inside the focus looking, it's kind of like a funhouse mirror. It's curved, but you just see yourself right side up. But if you're outside of the mirror and you're looking in here, what happens is the light rays kind of switch sides. I don't know if I'm drawing this very well. The light rays switch sides, and so you see someone upside down. I mention all this because, you know, we're talking about these very abstract. We're going to talk about polynomial functions, second degrees, which are parabolas. I guess I could state a parabola is actually just a curve like this. If you spin it around, you get a paraboloid, which is the shape of the mirror. But I thought, you know, this is not just some abstract thing. This is something we use in the real world. If you're interested in optics, you know, we talk about, even though it's a mirror, we talk about it as a lens because it focuses light. If you're interested in optics, you might know that most camera lenses, the surfaces are part of the sphere. These also can be concave or convex. And because of the feature of different materials, glass, when light hits the surface of these, it bends. We have something called refraction that happens. And these also will, you know, focus light, you know, like in a camera lens or in the other kind of telescope we call a refracting lens, refracting telescope. So again, I just wanted to bring that up so that maybe this will seem a little more part of the real world. A few days ago, we went over second degree polynomials, which of course are parabolas, and I felt like something was missing from that. Just discussion, so I wanted to add a little more. So there's some notes here. Now we'll where they are. There we are. All right. I decided to talk about mirrors a little. So, where does this come in? Where does this idea of a focus come into math? You may or may not have run into this description of a parabola before. This is kind of a geometric description, which is you have a point, which we call the focus. And for right now, I'm putting it above the origin. And it has some length, so I'm going to call that P. So it's at the point 0P. And we have another object, a line, which is on the other side of the x-axis, called, has anyone run into the name of this before? It's called the directrix. And we define a parabola as the locus. That's just a geometry word meaning collection of, set of points. That, well, let's pick some point. That's y. These are points that have the property that the distance from the focus and the distance to the directrix are equal. Doesn't look that way in my diagram, but that's okay. So to get the equation of this parabola, it's going to kind of look like this. We can just use that fact. Well, now we need to figure these things out. So we need to know the distance between 0P and xy. And here you can kind of see that the distance from this point down to the directrix is just going to be this distance P plus whatever our y coordinate is. So what's the distance between 2 points? We have a formula for that, right? It's on the exam. It's going to be the square root of 0 minus x squared plus p minus y squared. And we can take this and we can simplify it and play around with it. Let's square both sides. Negative x squared is just x squared. I'm just going to expand p squared minus 2py y squared. And since I'm squaring this, I get p squared plus 2py plus y squared. And you can see right away there's elements on both sides I can subtract out. P squareds go away, the y squareds go away, and I can add 2py to both sides, and I get x squared equals 4py, or in the usual form we would write it y equals 1 over 4p x squared. So this is just a constant, some number, where p is that distance of the focus from the origin. And there's my my equation, y equals x squared, that we're used to. There's some nice information here. If you think about our general form, y equals ax squared plus bx plus c, you can see right away these are the same coefficient, which means if you have a function in this form, you can tell right away where the focus is, because a is going to equal 1 over 4p, or if you like, p is going to equal 1 over 4a. Just a nice little piece of information if you're happen to want to know where the focus is, or happen to want to know where the direction is. Yes. Okay. All right, that's most of what I want to say about parabolas per se. There's something else I wanted to throw out, which the book doesn't really say much about it. It will come up later in a certain type of problem. But I wanted to say something about polynomials in general and what we can do with them. Polynomial is, we'll just say a to the n, x to the n, plus a to the n minus 1, n minus 1 plus all the way to a1x plus a0. We think of these x's as a variable representing a number. But they're really kind of an abstract thing. We're used to like looking for what number you plug in, what value. But all the things we've been doing with these polynomials, you can extend a little. You kind of branch out and I'm going to show you why this might be useful. So let me first note, something really obvious. If I take x minus a times x minus b, I have an equation where that's equal to 0. That immediately tells me the roots. That tells me that either x equals a or x equals b roots, solutions to this equation. Well, what if instead I substitute for x some function? Well, by all rights, that should tell me is that either f of x equals a or f of x equals b are solutions to this. Now, I haven't said what f of x is. I did, that's another problem. F of x equals a plus x. But you can see right away this is a solution. So how might that be helpful? Well, if I saw a problem like this, fourth degree polynomial, we don't have a general method to solve those, do we? But it looks suspiciously like we have x squared plus 3x squared plus 2 equals 0. X squared is a function, right? And just as if this were an x, it looks like I can factor it using reverse FOIL or quadratic formula, ED. You want to FOIL that, you'll see, you get f of x squared. The first, 1 plus 2 times f of x, 3f of x. And 2 is the constant. So going back here, this tells me that f of x plus 1. I hate when I do this. Really wanted a minus sign here. It's going to make everything happy. All right, there we go. F of x minus 1 equals 0. What was f of x? It was x squared. So here x is plus or minus 1. The second term, f of x minus 2 equals 0. Well, that's f of x equals 2, x squared equals 2, or x equals plus or minus the square root of 2. So this is just a very general idea. Anytime you have a polynomial, you might want to look at it and say, is this idea going to help me deal with it? Later in the class, we're going to deal with some functions that aren't as easy to deal with, but we might have a similar situation. We're gonna after the midterm, we're going to start doing some trigonometry, and I suspect a large number of you will run into something called sine of x. You don't need to know what it is. It's a function. It's some function. Well, if you saw an equation like this, I guess I'll write it this way for now. You might immediately go, oh, I don't know what to do with that. And again, if you think of this, again, it's just some general function. We can use our knowledge of reverse FOIL, quadratic formula. And here we have two equations that we can work with. All right, that's just me catching up. This last try here is Oliver Gilcher is not here, correct? Okay. All right. Any questions about this or anything else that's popped into your head? All right, just take a deep breath. We're going to be looking at dealing with more complicated polynomials than second degree. We're going to look at graphing them. And you certainly are encouraged to use technology, to use a graphing program. I think you have a calculator with a graph. You can use that. If you have a computer available with the internet, go to desmos.com is a good resource. I'm sure there are many others. If you have a Mac, you have a program on there called Grapher. If you haven't looked at it, you should check it out. It's fun, actually. But we're going to look at some details of polynomials. And polynomial AN x n plus AN minus 1 minus 1. And in particular, we're going to look at something called the end behavior. So, if I'm looking at a polynomial, I'm looking at the graph of a polynomial. What do I mean by the end behavior? Well, what I mean is, if you go out far enough, whatever the polynomial is, it's going to start acting in a very obvious manner. It's either going to be going up or down. Likewise, if you go far enough in the negative direction, it's going to be going up or down. Now, why is that? Well, we're putting a large number into the polynomial. This first term here, the leading term, it's x to the n, which is going to be 1 greater than whatever you have after it. So if you start putting bigger and bigger numbers, eventually this term is going to dominate. Eventually it's going to be as if these terms don't exist. They're just, they're just a small part of the value. So we only have to look at the first term to understand end behavior. And in particular, we want to look at this leading coefficient. So there's two possibilities. It's either less than 0 or it's greater than 0. Now there's one other thing you have to keep in mind, which is degree of a polynomial. N could be even, or n could be odd. So let's just look at a simple example that we know pretty well. Y is x squared. The polynomial is even, and the leading coefficient is positive. And that's just a parabola that looks like this. So the end behavior here is, it's going to go up, right, in both directions. If the leading coefficient is minus, then, it's just upside down, and as you go outward, the end behavior will take a breakdown. It's going to go down. Well, it's half the story right there. Just before I erase that, I wanted to say, well, why does it go up when we go negative? Well, because we're squaring. You square a negative number, you get a positive number, right? I want to contrast that with x cubed. I hope by now you have an idea it kind of looks like this. Well, unsurprisingly, as you go positive, it goes up. That actually happens irrelevant to the degree, right? Positively leading term as you go in the positive direction will always go up. But in the negative direction, because it's odd, you multiply a negative by itself an odd number of times, you still have a negative, so it's going to go down. And if you think about it for a minute, if we look at an odd degree polynomial with a negative leading coefficient, it's just going to be the opposite. All right, why don't we stop here for a few minutes, take a break, and we'll come back and we'll. Hello. All right, so we could do a little chart here. Leading coefficient. This is for all polynomials. Leading coefficient greater than 0 or less than 0. And we could have the degree of the polynomial even or odd. And we have what happens when x gets large. What happens to f of x? Well, it's positive, and the leading coefficient is even. This is going to get large. If it's less than 0, but the degree is even, what happens? It gets small or large. It's larger, yes. Does? Wait a minute. Do you agree with that? The leading coefficient is negative. Your degree is even, x squared or x to the fourth. What happens is, as you go off to the right? It's going down, isn't it? What happens as you go? It's negative. What happens as x gets very small, as that goes off to the left? Go up or down? You want to think about this because you won't always have the chart there for you. You can memorize the chart, refer to it, write it on your notes, but someday you might have to think for yourself. An opportunity to try it. What happens if the leading coefficient is negative, the degree is even, and we're going off to the left? Which direction does the function go? Anybody with me on this? You got a coin, you can flip it, and you got a 50-50 chance. Oh, that's probability statistics, we're not learning that today. Oh, but leading coefficient was negative. Which was that? That's the parabola upside down. This is going to go negative. What happens when the leading coefficient is positive? It's even, and we go to the left. Everybody has fixed it. Anybody else has any idea? Well, this is the simplest concept today. It's larger. This is the parabola. This is even. Both of them are going to go up, whether you're going left or right. So if it's odd, you don't even have to go all the way to x cubed. You just go to x, right? That's odd. That's just a line. The leading coefficient is positive. That's positive slope. That's easier to think of. So as you go to the right, it's going to be positive. As you go to the left, it's going to be negative. But if the leading coefficient is negative, you have a negative slope. And the results will be just the opposite. Okay, well that's useful if you're trying to graph something, you know, what is it doing off the ends? So, we have some, let's make up something here. So I'll copy something. Negative leading coefficient, odd, we know right away. So we go off in the positive direction, it's going to be going down. In the negative direction, it's going to be going up. So now we have to contend with what goes on in between. So, important feature over here in the middle is the zeros. Places where the function goes through the axis or it touches the axis. So I'm going to make some statements that are all equivalent about the zeros. First statement is C is a zero. That is the x value is C, y value is 0. p of c is equal to 0. Nice. Plug that c into the polynomial, you'll get out 0. X minus c is a factor. And the fourth item, which specifically has to do with the graph, like I stated before, c is an intercept. Now, I want to make one thing clear. The word intercept sounds like it goes through it. When we're dealing with y-intercepts, that's always the case. But when we're talking about an x-intercept, it could go through the axis, or as in the case of our parabola, y equals x squared, it doesn't actually go through, it just touches at 0. There's a little pearl of wisdom here. What are the roots of y equals of x squared equals 0? We'll see there are two roots, but they're both 0, 0. 0 and 0. They're the same number, but they count twice. And when you have a root that is like this, it's the same number, it counts twice, you'll get this type of situation where the graph will touch the x-axis, but it won't go through it. Okay. So we have some end behavior. We might go through the axis, and then we have some other end behavior. We have some zeros. Between any two zeros, because polynomials are smooth, you're going to have what we call local maximums and local minimums. This function, because it's odd, is going to go all the way from positive infinity to negative infinity. Its range is going to be complete. If it was even, it might have a minimum, which is the minimum, absolute minimum. But these are just local. Nearby, there's a value greater here, nearby, there's a value less. There's some value that's the minimum. So polynomials of higher degree are going to have more and more of these. They don't necessarily have maximums and minimums. For example, you want to graph function y equals, say, x to the 5th. It's going to look sort of like this. Well, all the roots of this are the same. They're all 0. And that's, to some degree, the cause of this. It has 5 real roots. Sometimes a function will have a minimum, a local minimum, even though it doesn't have a real root. But again, just understand this idea that as, between the ends, the function will move up and down, and we have these max and minimums. Okay. example here where we're going to try and graph something. So the function is x cubed minus 2x squared minus 3x. Usually, the first thing you should do when you're faced with this type of problem is you probably want to factor it. See if you can factor it easily. You can see immediately we take out a factor of x. And then if we look at this, we can think, can we reverse FOIL that? So it's going to be 3 and 1 if we can. It's minus 2x, so it's going to be minus 3 and plus 1, which means it has zeros or roots at 0, minus 1, and 3. And what's its end behavior? So they go off to the right, what's going to happen? We go up. So they go off to the left, what's going to happen? Okay, I'll take that and go down. So, okay. We can just plot these roots. 0, negative 1, 3. Since I know it doesn't have any roots beyond 3, and I know the end behavior is to go up, I know from this point on it's going to go up. Okay? I can say the same thing down here. I know there's no roots to the left of minus 1, so I know the graph's going to go down. And I know it goes through the axis through these 3 points. So there's going to be a local maximum here, a local minimum here. Now, I haven't taken any steps to identify points precisely. You can do that. You can plug values in. You can use your calculator to do that. You can look at a graph from a graphing program. It's just, to get some idea, we plug in 1/2. Right, so 1/2 cubed is 1/8, minus 2 times a 4th is a half, minus, wait a minute, did that wrong. One and a half is 3/2, so this is 27/8 minus 2 times 9/4 minus 9/2. That worked out right? No. So it's 27/8 minus 9. This is about 4 minus 9, about negative 5. So it's actually pretty far down. This is coming. And you can do the same for this point here to get some idea. All right. I already mentioned this issue where you might have a function with some duplicate roots. So this has 0 4 times, 2 3 times, and negative 1 2 times. 0, 2, and negative 1. We can look at the end behavior. This is 4 plus 3 plus 2, 9, that's odd. And the leading coefficient is positive. So, you know, from here it's going to go off this way, and from here it's going to go off this way. What does it do in between? Well, 0 appears 4 times, an even number of times. So that means it's actually not going to pass through. It's going to go down. I'm using the wrong one. I guess I want to do negative 1 first. Negative 1 appears 2 times. It's even, so it's not going to pass through. 0 is an even number, so it's also not going to pass through. But negative 2 is an odd number, so it is going to pass through. And again, you know, you could pick some points down here to try and find where the local max or min is. Same thing with this minimum here. We've got a local minimum here, local minimum here. We actually have 2 local max here, which we know are both 0. This kind of comes up to the axis. So these are all strategies you can use to produce a graph. And, you know, it gives you some information about features of graphs. All right, are there any questions about this section? There'll be a homework assignment where you can practice some of these features. All right. Yes, I think good for me to mention this was section 3.2. There'll be some things, if you take a look at that. Text in that section. Sure, they'll give you some other ideas I haven't mentioned. Things I just don't think are as useful. All right. Now, whether you're graphing or not, one of the important things you're going to learn to do with a polynomial is find its roots or its zeros. And we're just going to talk a few minutes about the real roots or zeros. This is section 3.4. So if you had a polynomial, and I defined it as x minus 2 times x minus 3 times x plus 4 equals 0. You know immediately that the roots are going to be 2, 3, and negative 4. If I multiply all this out, I'm going to get x cubed minus x squared minus 14x plus 24. Something you might take note of is that the constant term here, 24, is a number divisible by all three of these roots. But that doesn't seem like a coincidence. If I were to take some terms, x, a0x plus b0 times a1 x plus b1 times a2 if I multiply this all out, there's some end terms and some middle terms. I'm just going to pay attention to the end terms. They're going to be a0, b0, a0, a1, a2, x cubed, that's some intermediate terms, b0, b1, b2. Well, that explains why these divide this. However, the roots to this, this polynomial, they're not quite so simple. It would be x equals e naught over a naught. Well, in my example here, all the a's are 1, so that makes it simple. But in a real world situation, you might have to consider this. That is, these roots might be a factor of the constant term divided by the leading coefficient. Now, let me state a real important theorem here. And I guess what I want to make clear is that this is true of these roots, which happen to be rationals. There may be other roots that are not rationals for which this does not apply. The theorem is called the rational root theorem. And given some polynomial, equation, it limits the possible rational roots of this equation. Specifically, it says that any rational root, the numerator will be a factor of the constant term, and the denominator will be a factor of the leading coefficient. I think it's easier to explain this in terms of an example. Let's say I want to find out if there are any rational roots to this equation. Well, the constant term is 2, so its factors are 1, 2, and we're going to need to include negatives. The constant, the leading coefficient is 1, which only has one factor, 1, but we have to include -1. So we can look at this and we can see what are the possible roots here. Well, there's 1 over 1, negative 1 over 1, 2 over 1, and negative 2 over 1. So we know that if we try each of these roots, they'll either be a root or they won't. But there won't be any other rational roots. Now, this can get a little tedious, but it still can be really useful. Let's take a more real-world kind of example. Let's take 2x cubed. Doesn't matter what's in the middle. 6. So we have 6. Its factors are 1, 2, 3, and 6. I'm just going to put plus or minus here. And we have 2. Its factors are plus or minus 1 and 2. And now we just have to take all these combinations. 1, 2, 3, 6, negative 1, negative 2, negative 3, negative 6. 1/2, well, 1's a repeat. 3/2. I guess we already have 3. Negative 1/2, negative 3/2. So you have 2, 4, 6, 8, 10, 12 to choose from. And we don't necessarily have to check them all, we just have to hope we're going to get lucky. Right? So I could try 1, that would be 3 minus 13 plus 6, that doesn't work. We'll try 2, that would be 16 plus 8 is 24. No, that's not going to work. We can just keep going through the list. Once we find one, we're no longer in the same place. We can use the fact that if some c is a root, we can divide by x minus c and significantly simplify what we're doing. Obviously, we can stop here.